In Chapter 9, you're starting to learn some specific recipes. Your goal is to become a sort of molecular chef, and there are certain recipes that you need to know in terms of molecules. Just like if you were becoming a regular chef, there are certain recipes you need to know. For example, how to make a souffle or how to make a broth for a soup, so that you can use those to build in new contexts, to create your own dishes. And the first of these, perhaps even the most simplest, is called hydrohalogenation. So we see that name here. Now, you'll notice the names for these different recipes are long, but they're long because they're really descriptions. They're telling you exactly what you're doing. And they're descriptions with all the words in the description just smushed into one word. So it looks like a long, complicated word, but actually it's a really straightforward description. With hydrohalogenation, you're going to be adding a hydrogen. Oops. And you'll be adding a halogen. Oops. And that's usually symbolized by a capital X. That's going to be fluorine, chlorine, bromine, or iodine. But because fluorine is so small, about the size of a hydrogen, it is unable to handle a negative charge, and it doesn't usually show up in reactions because it can't handle its charge changing, like the other halogens can, because they're really big. So we're going to be adding those two things, and so if you look at these recipes, you're going to see H in one of those halogens, bromine. You look at the next one, H in one of the halogens, chlorine. And you look at the next one, H in one of the halogens, chlorine. So those are all hydrohalogenation reactions. Okay, now when you think about hydrogen being bonded to one of the halogens are all the way on the right on the periodic table, and so they're really electronegative. So they pull electrons to themselves, become slightly negative, and the hydrogen becomes slightly positive. Okay, so that's a distinctive feature, a recurring pattern in those, when you're in the hydrohalogens, when you're using those to do a hydrohalogenation. So you'll always have a hydrogen and a halogen when you're doing hydrohalogenation, and the other thing you need is an alkene. Now in this case, it's this six-membered ring with a double bond. The crucial thing to recognize with alkenes is that you have extra molecular glue. The electrons are like molecular glue that stick atomic nuclei together. And where you have a lot of electrons, you have a lot of chemical possibilities open to you. There's a rich chemistry there because you have a lot of extra molecular glue that you can use to stick new atoms onto the molecule. And so alkenes have a lot of extra electrons. They've got that extra pi bond, the second bond there. Remember, the first bond you ever form is a sigma bond. Every bond after that is a pi bond. So these double bonds have one sigma bond and one pi bond, and that the extra electrons in those pi bonds can be used to help stick these new things onto the molecule. Okay, well in this case, they want us to draw a mechanism. You see the word mechanism, and instantly you should think, okay, I have to use curved arrows to show the movement of electrons, to show step by step how this starting material turns in to this product. Now suppose you've never seen this reaction before, and you're trying to make sense of it. Anytime you ever are stuck in trying to make sense of a reaction, identify the nucleophiles and the electrophiles. Because reactions happen when opposite charges attract. The negative charge on a nucleophile is attracted to the positive charge on an electrophile, and that makes the reaction happen. So that you recognize a nucleophile because it will have at least one of four different characteristics. It could have a negative charge, full negative charge. That'll be easy to see because it'll be written in. It could have a partial negative charge. That's harder to see because it won't be written in. You're looking for differences in electronegativity there. It could have a lone pair because you have extra electrons that are exposed to the outside world in one direction. Or you could have a pi bond, extra electrons. Now I want to note that this lone pair and the pi bond themselves do not have a full negative or a partial negative charge on them. Without having a formal charge, they are without having a charge at all. They are nucleophilic because, in the case of the lone pair, they are electrons exposed to the outside world, And in the case of the pi bond, there are a lot of electrons stuck in one place. So even though they don't have an overall charge, they are still nucleophilic. For electrophiles, you'll recognize those because they'll either have a full positive charge, that'll be easy to see because it'll be written in, or a partial positive charge. That'll be harder to see. You have to know the differences notice differences in electronegativity to see that. So for example, this hydrogen is slightly positive because it's bonded to a much more electronegative atom. Okay, so if you ever get stuck in mechanisms, this table is the table that you want to refer back to. Look for the opposite charges. The opposite charges are going to want to attract. Now in this case, what they're giving us is hydrogen bromide. So let me replace the X here with that specific halogen, that bromine. And the charges that we found there apply, right? The bromine is all the way on the right in the periodic table. It's much more electronegative than hydrogen. So it steals the electrons for itself, becomes slightly negative, and the hydrogen loses those electrons and becomes slightly positive. So we have an electrophilic atom and a nucleophilic atom on that molecule. Well, that's going to be reacting with this. So let's go step by step and think about that ring. Where do we have nucleophilic centers? Do we have a full negative charge anywhere here? No, it would be written in. Do we have a partial negative charge? No. We only have carbon and hydrogen, and those have about the same electronegativity. Notice that the pi bond does not have a partial negative charge. Do we have a lone pair? No. Those would be written on a heteroatom. If you have a lone pair on a carbon, then it would have a full negative charge. Do we have a pi bond? Yes, we do. And so here, this pi bond is going to be our nucleophile. We could go through the same steps and see that there are no electrophilic centers in that atom. There's no full positive charge, and there's no partial positive charge here. So this can only function as a nucleophile. And there is only one electrophile for it to attack. And so the pi electrons swoop in, attack the slightly positive hydrogen. Hydrogen can only form one bond, so if it's going to form a new bond there, the electrons that are in the bond have to snap back onto the bromine, the most electronegative place nearby. So this is our first step. Now one thing we're definitely going to get out of this, and this bromine starts by having 3 lone pairs, it's going to end by having 4. So one thing we're definitely going to get out of this is a bromine with a full negative charge. So that's a pretty intense looking nucleophile. It's got the negative charge and the lone pairs. Now for the other molecule, it's a little tricky because the pi bond, the pi electrons, were on 2 different atoms. They were on the atom on the end and the atom toward the ring. So where does the hydrogen go? Does the hydrogen go to the carbon on the end? In which case, the carbon toward the ring is missing those electrons now. So let me actually color those electrons so we can follow where they're going. So if those electrons go on the end to bond the hydrogen on that far branch there, then the carbon in the middle is going to be missing the electrons that it had, in which case it will have a full positive charge. Or you could imagine that the hydrogen, instead of going on the end, goes in the middle, in which case the carbon on the end that had those red pi electrons is missing them now, and so it has the positive charge. So those are 2 possible products. However, you only get one. Which one? Well, think about the stability of these 2 molecules. The unstable thing about those molecules is the charge. There's a full positive charge. Those are on a carbon, so you have carbocations. Which carbocation is more stable? This one here, that carbon is bonded to, this carbon is bonded to 1, 2, 3 other carbons. So that is a tertiary carbocation. This carbon is bonded to just 1. So that is a primary carbocation. Tertiary carbocations are more stable than primary carbocations, and so we do not observe this bottom product, we only observe the top, more stable product. even if you imagine this forming, it would quickly do a carbocation rearrangement to give you this top product. Okay, so notice here, the hydrogen goes to the less substituted carbon. So the pattern we're seeing here is that the hydrogen goes to the less substituted carbon. And whatever the other thing is that's going to add will go to the more substituted carbon. Now, we're going to see these double bonds reacting with a whole bunch of stuff. We're going to add stuff onto them. And these two possibilities will recur very often. You'll have a possibility where one of the things you add goes on the less substituted carbon, and the other thing you add goes on the more substituted carbon. And so this pattern of a hydrogen going to a less substituted carbon anytime you form a carbocation, that pattern has a name because it recurs so often. That name is Markovnikov's rule. So if a reaction is Markovnikov addition, then you will be adding a hydrogen to the less substituted carbon. And whatever the other thing you're adding is, in this case it's going to be bromine, that will go to the more substituted carbon. But in Markovnikov addition, hydrogen goes to the less substituted carbon. Okay, I want to emphasize that because it's going to come back a lot. All right, so let's set this rule aside. We'll use it later for sure. But if we just think about these two products that we get after this first step, how will they interact with each other? And your first reaction, and a fair one, may be, I have no idea, I've never seen these molecules before. How would I know? But always, anytime you get stuck, think back to this table of electrophiles and nucleophiles. 95% of all reactions in organic chemistry happen because opposite charges attract. Nucleophiles attack electrophiles. And here we only have one nucleophile and we only have one electrophile. And so the nucleophile attacks the electrophile. And the product that you get after that is that. Okay, so notice the overall thing. We added, as we said at the very beginning, we added a hydrogen and we added a halogen. So this is hydrohalogenation. If you're comparing the overall change in the molecule, a double bond turns into a single bond. And the hydrogen goes on the less substituted carbon in hydrohalogenation because this is Markovnikov addition. You're forming the most stable carbocation. That means the carbocation has to be on the more substituted position, so the hydrogen has to go to the less substituted position. And otherwise, this is the complete mechanism for this hydrohalogenation. Okay, let's take some of these notes that we've built here and think through that same mechanism, just with a different specific carbon chains, different specific halogens. Okay, so we have our alkene. This would be 3-methyl-2-pentene, this alkene here. And we're going to treat that with hydrochloric acid, or hydrogen chloride if it's a gas. That's this. If it goes into water, it turns into hydrochloric acid. That's the acid that's in your stomach. Okay, so if you were to ingest this molecule, what would it do when it gets into your stomach acid? Well, at first you may say, I have no idea, but anytime you get stuck, identify the nucleophiles and the electrophiles. And let's think about nucleophiles first. In this molecule on the left, there are no full negative charges. They would be written in. There are no partial negative charges because you have to have big differences in electronegativity. And here, we only have carbon and hydrogen, which have about the same electronegativity. We don't have any lone pairs. Those usually show up on heteroatoms, like oxygen or nitrogen, atoms that are different from carbon. If carbon has a lone pair, then it has a full negative charge, which we don't see here. And we do have a pi bond. This pi bond right there, that is going to be a nucleophile. So let me draw that in red to emphasize that. So that is, this molecule has only one nucleophile. That is, those are the pi electrons. As far as electrophiles go, we don't have a full positive charge, that would be written in, and we don't have a partial positive charge because that would require two atoms with differing electronegativity, which we don't have. So we know already this has to function as a nucleophile. Okay, let's go through the same procedure in hydrogen chloride. We don't have a full negative charge, that would be written in. We do have a partial negative charge. The chlorine is right underneath fluorine. It's almost at the top right of the periodic table, extremely electronegative, pulls electrons to itself and becomes slightly negative, which, by the way, means that the hydrogen is losing electrons and becomes slightly positive. Okay, next, lone pairs. We do have lone pairs, actually. This chlorine has 1, 2, 3 lone pairs. And pi bonds, this molecule, hydrogen chloride, does not have any pi bonds. Okay, well, we have two nucleophiles, one on the molecule on the left, one on the right, but there's nothing in this carbon chain for this chlorine nucleophile to attack. So our nucleophile has to be the pi bond in this carbon chain, and there's only one electrophile for it to attack, this hydrogen. So the pi electrons swoop in, stick to the hydrogen. Hydrogen can only form one bond, so if it's forming this new bond, that kicks those electrons off. They go to the most electronegative place nearby, which is the chlorine. All right, well, one thing we know we're going to have is chlorine with those 3 lone pairs it had before. It's going to have a full negative charge, and the 1 lone pair that it's getting from the bond. That's our chlorine. Now the other thing, we have our carbon chain. We didn't add or remove any carbons, but we have to think about where the hydrogen is going to go. These pi electrons are on 2 different carbons. They're on this carbon in the middle and this carbon sort of toward the right. So where does the hydrogen go? If you think about the 2 possibilities, the hydrogen could either go to the carbon on the right, in which case the carbon on the left is missing those electrons now and has a positive charge, or the hydrogen could go on the left, in which case the carbon on the right is missing those pi electrons and would have a full positive charge. Well, notice that this carbocation here is 1, 2, 3, bonded to 3 carbons, so it's tertiary. And the carbocation below it is bonded to 1, 2 carbons, so it is secondary. A tertiary carbocation is more stable than a secondary carbocation. It can borrow electrons from more neighboring carbons than this one can. And so that's the one you form, the more stable carbocation. In other words, the hydrogen goes to the less substituted carbon. And this, as we saw before, was Markovnikov's rule. Hydrohalogenation is Markovnikov addition of H and X. It means H goes to the less substituted carbon. Okay, so we don't get this product at the bottom. Well, at this point, we have a clear nucleophile, the chlorine, and we have a clear electrophile, the carbocation. So the full negative charge in the chlorine, those electrons swoop in and they attack the full positive charge on the carbocation. And you end up with this molecule here. Now, sometimes people don't draw the hydrogen in because it's implied in a skeletal formula, but you're more than welcome to keep it in there. You do have to draw it in throughout the mechanism, but once it's on the carbon chain, you don't have to. You don't have to keep it there in the final product if you don't want. You notice that they don't draw the hydrogen in this product here. So let's zoom out for a second and look at the overall process. We have the double bond, and we're adding 2 things, hydrogen and chlorine. The hydrogen adds, so it's hydrohalogenation. hydrogen and the halogen. We added those on the 2 carbons in the double bond, and the hydrogen goes to the less substituted carbon because it's Markovnikov addition. So this carbon is secondary, this carbon is tertiary, the hydrogen goes to the less substituted carbon. Also, one thing that it's useful to do, and I want to go back after we do this for this reaction and just quickly fill it in for the previous one. When you're learning these mechanisms, always write down the curved arrow patterns that they have. It's easier to remember things when you put them into groups, and instead of trying to think of this as lots of individual arrows, it's useful to recognize that this is really a proton transfer. You're changing a hydrogen, a proton, is leaving one molecule and going to another. And the second step is nucleophilic attack. You have a strong nucleophile attacking an electrophile. So these hydrohalogenation reactions, the ones we've seen so far, proton transfer followed by nucleophilic attack. It's especially useful to build up this habit now of filling in these curved arrow patterns, because now the mechanisms are not too long. But as you get into organic chemistry 2, the mechanisms can be 8, 9, 10 steps long, and knowing these curved arrow patterns, being able to summarize them in this way will help you to remember the mechanism much more easily. So I would encourage you to practice doing that now. So notice again, hydrogen is leaving one molecule, going on to another, and so that's a proton transfer. And in this one, we have a negatively charged bromine attacking a carbocation. That is nucleophilic attack. Okay, let's draw one more in for this. We're going to draw the mechanism here, and we'll use the same sort of tools, the same tables that we've built up before. Okay, well now we should be seeing patterns, but let's say you take your alkene with that extramolecular glue, those pi electrons, and you react that with hydrogen chloride again. So if you put that in water, it's hydrochloric acid, which is your stomach acid. It pushes and pulls on the food that you put into your stomach to rip it apart so it's easier to digest. Okay, well, first let's try to identify the nucleophiles here. We don't have a full negative charge. We don't have a partial negative charge because we don't have any big differences in electronegativity. We only have carbon and hydrogen in that molecule, and those have about the same electronegativity. Carbon is tiny, it's just a smidge, a hair larger, more electronegative than hydrogen, but they're about the same. There are no lone pairs. If carbon has a lone pair, then it has a full negative charge, and we don't have that here. But there is a pi bond. There's a pi bond right there. So we're going to draw in that pi bond as a nucleophile. If we think about that same molecule from the perspective of electrophiles, we don't have a full positive charge, we don't have a partial positive charge. So that molecule is clearly going to be acting as our nucleophile. It's all it can do. If we go through the same procedure for the molecule on the right, the hydrogen chloride, we don't have a full negative charge, that would be drawn in. We do have a partial negative charge. The chlorine is really electronegative. It's in the top right of the periodic table, pulls electrons to itself, so it becomes slightly negative, and that means the hydrogen is losing those electrons and becomes slightly positive. There are lone pairs. The chlorine actually has 3 lone pairs, 1, 2, 3. So that's looking like a nucleophile, and there's no pi bond. So much for identifying nucleophiles there. How about electrophiles? We don't have a full positive charge, that would be drawn in, but we do have the partial positive charge because of the difference in electronegativity, the hydrogen. Okay, well these are the molecules we have to work with, and even if you forget the mechanism, you can remember that these opposite charge, these nucleophiles attack the electrophiles. Well, there's only one way this molecule can react. That can only react as a nucleophile. There's nothing for the chlorine to attack there. And there's only one electrophile for it to attack. So those pi electrons swoop in, smack into the hydrogen, stick to it. The hydrogen can only have one molecule it's attached to, so So if it's forming this new bond, the bond it already has breaks, those electrons go onto the most electronegative place nearby. And you'll recognize this as a classic proton transfer. So after that step, we're definitely going to have a chlorine with a full negative charge. It has the 2 electrons that it just got from the bond, plus the 3 lone pairs that it had before. That gives it a full negative charge. So that's looking like a strong nucleophile now. Next, we have our carbon chain. Now all the carbons are still going to be there. We're not adding or taking away carbons. But we have to think about where to add the hydrogen. Now at this point, you may just remember that hydrohalogenation is Markovnikov addition. So the hydrogen is going to go to the less substituted carbon. This carbon on the left is tertiary. It's bonded to 3 other carbons. Carbon on the right is secondary. And so you may just say, okay, the carbon is going to go to the carbon on the right in the double bond because that is the less substituted carbon. And that means you have the positive charge on the other carbon. However, if you weren't there yet, if you don't remember that this was Markovnikov addition, you can always draw both possible products and think through it. What if the hydrogen added to the other carbon? Well, in that case, the carbocation would be on the right. So which one of these is more stable? Carbocation here is bonded to 1, 2, 3 carbons, so that is tertiary. The carbocation below is bonded to 1, 2 carbons, so that is secondary. You could see that this is the more stable carbocation, so that's the one that's going to form. Even if this did form, it would quickly rearrange to this top one. In other words, Markovnikov's rule holds true again. The hydrogen because this is Markovnikov addition, you form a carbocation, the hydrogen goes to the less substituted carbon. And whatever the other thing is, it goes to the more substituted carbon. So this is what we have to deal with. We see that the carbocation is a strong electrophile, the chlorine is a strong nucleophile, and so the chlorine swoops in, attacks the positive charge, the carbon with the positive charge. And so that is classic nucleophilic attack. And what we end up with is this molecule here, which is what they gave us on top. Now notice they don't have the hydrogen written in because it's implied in these skeletal structures. All right, notice the overall change. We started with a double bond, we don't have it anymore. We used that glue to stick new stuff on the molecule. We have a hydrogen on one of the carbons in the double bond, and we put a halogen on the other one. So hydrohalogenation. And it's Markovnikov addition, so the hydrogen goes to the less substituted carbon. And whatever the other thing is, in this case chlorine, goes to the more substituted carbon. So again, we see the mechanism for this is just 2 steps, proton transfer followed by nucleophilic attack. Hopefully this helps clarify how you can draw the mechanism for a hydrohalogenation. It's just a basic, simple, straightforward hydrohalogenation.